All right, so here's a look at the data we got from our POGIL, which is a process-oriented guided inquiry learning activity, or guided inquiry lab. But we're given this data and we're going to figure out how to graph it, see what kind of graph it makes. Then we're trying to really find the acceleration of the object and talk about some other stuff. We end up developing some formulas, etc., that allow us to then do calculations with position, velocity, acceleration, and time, rather than having to resort to graphs and only use a graphical analysis. So here's my data. First thing we're asked to do is to graph it. So I've graphed those points here in red. And I have my first, second, third, fourth, fifth, and finally my sixth point up here. And then once we get that done, we draw that smooth curve. We look at what sort of graph is that. We should recognize that it's parabolic or a parabola. How do we describe the slope of the graph? Right? We would probably say it's positive the whole time, and it's always changing the whole time, right? It's positive and constantly changing or constantly increasing, right? Here my slope is going to be like 0, and as I go forward through there, my slope each time is going to be a little bit different. It's going to be getting bigger as I go through, right? So it's 0 initially, so it's positive and constantly changing. What quantity does the slope of a position or distance versus time graph give us? And here, example, position and or distance and displacement are the same thing. It's only going in one direction, right? It's rolling down a ramp. It's only rolling one direction. But what does that slope of position versus time or distance versus time graph give us? That slope should equal velocity. Okay? Now, in general, right about this object, it starts out and it starts at rest. I don't know if it tells us that or not. A wheel rolling from rest down an incline. So initially, our velocity must be 0, and then it's slowly getting faster and faster and faster. So it should be getting faster. It's not getting slower. It's not staying the same. How do you know? Because I've got a positive slope. And the slope is getting bigger. So on your position and time graph, draw a line which connects the points t equals 0 to t equals 6. So here you see I've drawn that line here, right? From 0 to t equals 6, I've drawn that line. And it says calculate the slope. Well, the slope should be 180 minus 0 over 6, or 30 centimeters per second. And I just used the endpoints of my data to do that. Normally, if we were doing a graph by hand, we wouldn't use the data points, but for this case, we're fine. What does the slope of that line represent? It's a slope of x versus t. So what should it represent? Some kind of velocity. All right, but if we look at the start of that, this is my slope, this is my velocity line. Was it going that fast right here? And was it going that fast right here? What have I done? All right, never mind. All right, folks, bear with me while I redraw this daggum. Bear with me while I redraw this curve. Oh my goodness. Now I've really done and botched it up. All right. So I'm going to do my best to redraw that curve right here. Just bear with me. Understand that it may not May not be exactly what it was, but it'll be good enough. So she'll have a point there and a point there. My other points should all still be there. We'll just deal with that and assume it's a smooth curve like I was just discussing. Now, so the slope of that line represents the velocity, but at t equals 0, it started out at rest, and here it's moving, so it can't be going the same velocity that whole time. So what kind of velocity is that, right? It's going slower than that speed. Anytime the slope of the curve is less than this, it's going less than that speed. So it's like at 3 seconds, right? The tangent line here is about the same slope as that. So this should be the average speed because it's going at different speeds during that whole time. Should be my average speed. Going slower from 0 to 3 and faster from 3 to 6. Right, so now I want to go back and draw a line or look at a line that's drawn between t equal 2 and t equal 4. And I already had that line on there, so regardless of what my curve looks like now, before when it looked all perfect, we should see that this line and this line have basically the same slope. They're parallel to each other. Okay, but this is from 2 to 4. This one was from 0 to 6. We calculate the slope of that line, and the slope of that line should still be 30, should be, let me see what it says there for my data points real quick. My data points should be from 2 to 4, so 80 minus 20. Over 2, which still should be 30 centimeters per second. All right, it should have a slope similar to this. They're parallel. They should be the same. All right. Now, lines 4 and 7 tell us about the speed of the wheel that during those two segments of time from 0 to 6 and from 2 to 4, right, the wheel has the same average speed between those 2 points. All right, so now I want to look at drawing a line that is tangent, right, to the curve at x equal 3, which I've already drawn here, and actually looks pretty decent for that part of the curve, and then I get all squirrely up there. But that line, tangent, right, think about if I made my interval from 2 to 4, if I went from 2.5 to 3.5, and 2 3/4 to 3 1/4. And 2.9 to 3.1. Eventually, as I made that gap smaller and smaller and smaller, eventually I would get a line that only touched in 1 point. But all those lines would be parallel to these initial lines. So here, you can see my line, right, drawn right here, parallel to this other line. So the slope of this must be 30 centimeters per second. Okay? Now, there's a little clue right here. Is there a name for the speed that an object has at a certain instant in time? It should be the instantaneous speed. The speed it has right now at this particular moment in time, right? We should see the slope of the tangent line is the same as the slope of those other two lines from 2 to 4 and 0 to 6. The slope of the tangent line tells me the speed at t equal 3 seconds, right? So at t equal 3, it's the same as the average over any interval where 3 is at the center. From 0 to 6, 3 is the middle. From 2 to 4, 3 is the middle. So now, basically what you're supposed to do on the graph then is to go back now and look at, determine the speed, the slope of a line from 0 to t equal 3. So if I take 0 to t equal 3, and I draw that line, although I probably don't want to have that. I probably want to be from 1 to 3. 0 to 3 is not going to do me much good. If I go from 1 to 3, we can see that a tangent line would be parallel to that. So the slope from 1 to 3 this should be from 1 to 3. Oh, no. Go from 0 to 3. That's fine. Go back. From 0 to 3, that average speed should be 45. No, what is it? Yeah, 45 minus 0. Over 3, which gives me the speed of 15 centimeters per second. All right. Well, what's the halfway point of that break from 0 to 3? Should be at 1.5, right? So my speed at 3 is 30. My speed where at a point where at the midpoint of the interval from 0 to 3 is 15. We're going to see if that holds. All right, so now it says determine the slope from t equals 0 to 4 and determine the slope of a tangent line at 2. From 0 to 4, I should be 80 minus 0 over 4, or 20 centimeters per second. And I'm supposed to determine the speed of the tangent line at t equal 2. Well, at t equal 2, right, we can take that, if we can take that tangent line slope from one of two ways. We can either say the slope from 1 to 3, or we can draw the tangent line. I'm going to take the slope from 1 to 3, use that bracket method that we already developed up there. So 3, it's at 45 minus 5 over 2, which gives me, what's that, 40 over 2, or 20 centimeters per second. Make sure I'm doing something right here. Slope from 0 to 4 should have been 20. Slope from 0 to 4 is 20. Slope at is 20. Tangent at 20. So those should be the same. 20 centimeters per second, 20 centimeters per second. So we can find the speed of an object under constant acceleration at any particular moment in time one of two ways. We could either draw a tangent line at t equal 2, pick some points on there and find its slope, or we can bracket it, or make it the center of a bracket and find the slope of that line, and that should give us that velocity. We should do that either way. So looking up the position time graph above, use either one of those methods, and you should come up with the speed that look like this. The last one, you can't use a bracket method. You've got to look at a tangent line, but you should be able to tell that it's going to be 60 just from the other data and the fact that it's a constant acceleration, so it's not going to change. And then you're tasked to find plot a graph of all those points. And I've just moved my graph, so hang on a second. Technical issues. Now we're good. So it should be at 0, 10, 20, 30, 40, 50, and 60. And then I should have used a ruler, made a nice straight edge there. Now, once I have that velocity, this is my velocity final graph and my time graph. This is the velocity at each one of those seconds. So it's like instantaneous velocity or the final velocity, right, of the object over that interval from 0 to 1, from 0 to 2, from 0 to 3. It's the final velocity there, right? So the slope of that graph should represent change in velocity over time, should represent acceleration. The acceleration should be VF minus VI over T. We can write an equation for it where we get VF equals AT plus VI. And that should be an equation of a line y equals mx plus b. Now in this case, my initial velocity equals 0 because it was at rest, right? The slope of this line should be my acceleration. I've got final velocity on the y-axis, time on the x. The slope of that line should be acceleration, right? And that's something that's a big point. That kind of verifies the fact that we've already talked about the slope of velocity versus time is acceleration. Now I want to look at the comparison. So I have at t equal 1, this is from the table above, they have 10, 20, 30, 40, 50, 50, and 60. Then I want to know, right, what was the speed at t equal 2? It was 20. What about at t equal 4? It was 40. What about at t equal 6? It was 60. So notice that at t equal 2, my speed was 20. Halfway, right, in that interval, right, where if 0 is one point and t equal 2 is the other point, at the midway point, the speed is half as much, right? If I look at the interval from 2 to 4, right, halfway between 0 and 4 is 2. The final speed at 4 is equal to twice that speed that you have at the halfway point. Same thing with 6 and 30, right? Or 6 and 3. At t equals 6, my speed was 60. Halfway to t equals 6, my speed was 30. All right, so that gives us the idea that, and we know that from 0 to 60, right, that at t equal 3, that was the average speed at t3. From 0 to 6, right, the average speed from 0 to 6 was equal to t3, or the speed at t3. The average was 30, the speed at 3 was 30. All right, so the initial velocity in this experiment is 0. Initial velocity is 0 because it's at rest. Now, how do we take the average of two numbers? We take number 1 plus number 2 divided by 2. So can we relate that to the types of velocity that we have? We have the final velocity and the initial velocity. So we have final velocity plus initial velocity over 2. That should give us the average velocity. So if now my initial velocity is 0, I get V average is equal to VF over 2, or 2 times V average is equal to VF. And is that what we set up here? This velocity, right, is my V average. At t equal 1, the average velocity was 10. At 2, it was 20. At 3, it was 30, right? So my final velocity there, at 6, my final velocity was 60. this one was 40, and that one was 20. This is a V final at the end of the interval from 0 to 2, or from 2 to 4, or 3 to 6, or 0 to 4 and 0 to 6, my bad. So this is my final velocity. This is V average. And does that make sense? So 2 times V average equals VF. Is that what we see right here? Yes, it is. 2 times 10 equals 20. 2 times 20 equals 40. 2 times 30 equals 60. And that should hold true for any situation where we have constant acceleration. So now we get 3 basic equations then. We get equation number 1, average velocity equals change in position over time. Average velocity equals VF plus V naught over 2. And a definition of acceleration. All right, so now we're going to look at those 3 equations, and we're going to develop some equations that we can use to do some math. So this is one of those equations that we want to use. It's called the position time equation. And we want to start with these equations over here and make some substitutions and figure out how we can get those equations to produce this one. So obviously I have a V average is what I'm going to start with. So V average should be equal to delta X over T, and it's also equal to VF plus V naught over 2. And that's like the little transitive property. If delta X over T equals V average, and VF plus V naught over 2 equals V average, then delta X equals over T equals VF plus V naught over 2. And then I'm going to take this equation, VF equals V naught plus A times T. And I'm going to substitute this value right here in here for VF. So I'm going to get delta X equals V naught plus AT plus V naught all over 2. And this should be over T. That's just called substitution. If I'm going to collect some like terms and get delta X over T equals V naught plus V naught is 2 V naught. I'm going to plus AT all over 2. That should be then equal to 2 V naught over 2 plus AT over 2. And that should all be equal to delta X over T. So I end up with, I'm going to multiply both sides through by T. So I'm going to get T times 2 V naught over 2 plus AT over 2 should be equal to delta X. And I end up with delta X equals 2 V naught over 2 is V naught. So I have V naught times T plus AT times T is AT squared over 2, which is 1/2 of AT squared. And that is known as the position time equation. And notice that it relates initial velocity, acceleration time, and change in position. A lot of times we see that written as X equals X naught plus V naught T plus 1/2 of AT squared. And you should see that up on the wall. If you're ever in the classroom, you'll see it up on the wall. All right, then the next question says, beginning with equations 1 and 2 again, rearrange it so we can get a look at this equation, which notice there's no time in this equation. So we should look at again, delta X over T equals VF plus V naught all over 2, and we have VF equals V naught plus A times T. And the equation we're looking for doesn't have T in it, so I'm going to have to solve this equation for acceleration in terms of time. So I get VF minus V naught all over A should equal time, and that's just a little algebra. So hopefully we can deal with that. And then I get delta X over VF minus V naught over A, which is T, should be equal to VF plus V naught. And this V naught and VI, remember the same thing. Sorry, it's my old school, over 2. So now I'm just going to do a little rearranging. I'm going to multiply both sides of the equation by 2 to get 2 delta x. We'll multiply both sides of the equation by VF minus V naught over A. All right, then I'm going to be crazy and multiply my A across the other side, so I get 2A delta x equals VF minus V naught times VF plus V naught. And from all those years ago in Algebra 2, we should recall that that must be a difference of 2 squares, so that must equal VF squared minus V naught squared equals 2A delta x. So now, just to rearrange it into a form that's more common, I'm just going to add V naught to both sides. So I get V naught squared plus 2A delta x equals VF squared, and then I flip it around. VF squared equals V naught squared plus 2A delta x, which relates initial and final velocity, acceleration, and change in position. So now we really end up with several equations that we can use, but we have VF equals V naught plus AT. VF squared equals V naught squared plus 2A delta x, and x equals x naught plus V naught t plus 1/2 of AT squared. And those are really the three equations we're going to need to deal with. Occasionally we would deal with this one for V average. But most of these would be these three equations that will allow us the definition of acceleration and two equations we develop from that using the definition of average velocity. And those three equations are going to allow us then to figure out pretty much anything we want to know about any kind of motion problem that we have in one dimension. And we'll spend the next couple of days looking at those problems and talking about that. And then we'll talk about objects that are going to be falling straight down or going straight up and straight down, similar to the ways we might go left or right on a number line or on a track. So that should be where we are. That should be Friday. We'll look at the problems and stuff tomorrow, but that should go over your POGIL activity. Hopefully you understand all that. If you don't, make sure you get a hold of me, and we'll talk about it and make sure you're up to speed. And then we'll talk about an easier way that we can look at changing this graph of position time, which is a nightmare of a graph to analyze by hand, as you can see. We'll talk about an easier way to deal with that with data using Accel, which is super easy. So be ready for that, and hope you all have a good one, and I'll see you.